Let us move to the third item in our list towards the generalization of the Basque-Coon equation. In the original Basque-Coon equation, we assumed that the amplitude of loading was fixed. And presently, we're going to consider cases where that amplitude can vary. In other words, the amplitude of the stress can change over time. In that case, we'd like to figure out how to estimate number of cycles to failure. And what we're going to look at here is just the sketch of an idea. So it's a sketch because ultimately one important aspect, sorry for the typo, one important aspect of fatigue is a careful counting of the number of cycles. So cycle counting can be tricky. And I'm going to omit the tricks that might be, or the important points that might be involved here. So I'll just note that cycle counting can be tricky. That's the first remark. That's why I call it a sketch. And we're emphasizing that it's just an idea because this idea is actually far from perfect. Just like any other proposal, it works to the extent that it's provided, that is supported by data, and it turns out the proposal that we are making has plenty of need for improvement. So, but let's sketch the idea anyway. Well, what we're going to suppose is just to simplify our life a little bit, just a single stress component, say a normal stress. So it's an intrinsically one-dimensional scenario, but let's say that it has both alternating and mean components. So if there was only one non-constant stress amplitude and therefore a constant mean as well, then I would just map this to an equivalent completely reverse stress amplitude and then estimate number of cycles to failure based on Basque-Coon equation. But now the point is that these values will vary over time. But they vary over certain intervals. They don't vary from cycle to cycle. It's just that, for instance, you start off with a certain stress amplitude, let's call that sigma A1, and with a certain mean in one interval of loading, and then after so many cycles, the amplitude changes and the mean as well can change. For instance, the amplitude can decrease only, the mean can remain a constant, but then in another, let's say after another, let's say 2,000, 3,000 cycles, the mean can shift and the amplitude as well can double, let's say. So there are three intervals so far, the first one, the second one, the third one, and so on. You can have several intervals. And now the idea is, well, if I had only this, I could estimate number of cycles to failure, and for that matter, if I had only one of any of these, I could estimate number of cycles to failure. But now I have all of them at the same time, and the question is, well, these keep varying, so how do I figure out when failure occurs? And the idea is the following. You pick one of these, say the jth one. Let's call that sigma aj and sigma mj. Okay, j could be 1, 2, 3, 4, whatever. And what I could do is, if I had only that, I could map them to a equivalent completely reverse stress amplitude, sigma arj. And sigma arj has its corresponding life that is predicted through the Basque-Coon equation. Let's call that NFJ. All right. So NFJ here, what it stands for is the fatigue life, assuming only the jth interval or the jth load applies. So if I had only, say, j equals 1, only the first one applying, this is how I would estimate the number of cycles to failure. I call that NF1. And then I do the same thing for 2, 3, and 4 because it turns out the load is not a constant. So now suppose you start with 1, but you don't cycle all the way to failure, but instead you cycle for a number of cycles, let's say nj, where nj is less than nfj. So that is the actual life spent in that interval of loading. So the keywords here is that we're just calculating NF, assuming that only that load applies, but then in reality, a smaller number of cycles are spent in that phase before switching to another amplitude and mean in general. So then we say that, well, a certain fraction of the life has been spent, and that fraction is simply the ratio of nj to nfj. For instance, that ratio could be 1 to 10, and then we would say that 10% of life has been spent in that phase j. Okay, now if I had only one loading and without switching, if I had stopped the experiment at the end of the first phase, indeed this would really mean the fraction of life spent in the first interval. But now we are going to estimate the fraction of life spent, overall life spent, within each interval by the same expression. In other words, we're going to say that somehow fatigue failure occurs ultimately because the amount of fraction spent accumulates towards 1. In other words, you accumulate a certain amount of damage over each interval, and that damage is calculated exactly like this, and when the total damage hits 1, you essentially spend all the life possible under these combinations of loads. So we're going to say that fatigue failure occurs due to accumulated damage. So this is of course just a proposal. There is no reason why in such complicated combinations of loads we should accumulate the damage in the following fashion, which is simply going to be a sum. One can propose different combinations of damage contribution from each phase. One can be more critical than the other, more substantial towards overall life than the other, but we're just going to say that, well, in the first phase, this amount has been spent. In the second phase, if it was applied by itself, you spent so much, and then I will just sum all of them. In other words, I will sum over j and j, the actual spent over the life that would have been observed if only that alternating and mean value was applied. I take that ratio, sum them, when it hits 1, life is over. In other words, we have fatigue failure. So this simple argument is called the Palmgren minor rule. So I'll put rule in quotes because, of course, it's just a model. It's just a proposal. Now, let us see how this proposal is helpful in deciding when failure is going to occur under complicated combinations of loadings. And for that, what I'm going to do is I'm going to take the titanium alloy shaft example that we just worked on, and I'm going to modify it in a simple way. All right, so what we are going to do is, as an example, we're going to take our titanium alloy example, and we're going to pose the question as follows. Well, remember in that example, there was a 0 to max loading given by a torque and a bending moment, and the question was, well, what is the total number of cycles to failure? And failure occurs, we determined, after 143,000 cycles. Now, But what we're going to now do is, what we're going to say is, we don't actually go all the way with this amount of load. We're actually only going to cycle for 50,000 cycles. And subsequently, the load, in other words, the torque and the bending moments, they are both increased by 20%. And the question is simple. What's the remaining life? In other words, we cycled 50,000 times, and then we increase the load by 20%. How many more cycles can we go through before failure occurs? So now let us proceed with the solution. The idea is the Palmgren-Minor rule. We only have two intervals of loading. First, we start with the original problem, and we eventually have already determined that we have 143,000 cycles applied that can be applied all the way to failure, but in reality now we're saying that we apply only 50,000. So this ratio now is the fraction of life spent under the original conditions of loading. And the question is now, after we increase, how many more cycles can we go through? And well, we're looking for a certain number of cycles. That's going to be N2. That's our remaining life. And that remaining life will be such that if I calculate its contribution to overall life, it's going to be such that we take the ratio of N2 over the number of cycles to failure if the second interval had been applied on its own. When the sum reaches 1, the total damage accumulates to 1 and we get failure. So this is what we are trying to determine. And in order to determine that, therefore, we first need to determine NF2. In other words, number of cycles only under the conditions of the second phase of loading. So in that case, we do need the completely reversed stress amplitude, the equivalent alternating stress and the equivalent mean stress associated with the second phase of loading. Now, for the first phase, we've calculated what they are. Okay. Now, the components of the stress that go into those expressions, they each scale with the torque and the bending moment that's been applied. So therefore, when I increase the torque and the bending moment by 20%, these two values will automatically be scaled by 20%. So in other words, if these are the equivalent alternating and mean stresses for the first phase, the second phase will be such that this will be multiplied by 1.2, that will be multiplied by 1.2. So that's just 20% increase. So in other words, 1.2 times sigma A 1, 1.2 times sigma M bar 2, 1. And this value is therefore 560.2 MPa. The second one is 366.7 MPa. Okay, good. Now, what I now need to do is go for the life. And to calculate the life, we need to calculate, we want to apply the Basquin equation, which says that sigma AR, the equivalent completely reversed stress amplitude for the second phase, is equal to the expression that we have already used in the previous case. Now, just be careful. Now we need to take these and map them to a sigma AR2, and we will again use the same expression, the Morrow relation, But notice that what will come out of that expression is not going to be 1.2 times the sigma AR value in the first interval. This comes out to be presently 683.7 MPa. Okay, so it is not equal to 1.2 times sigma AR 1. And the reason it's not scaled, although these are scaled trivially, is because, you see, in the Merrill relation, for instance, this is scaled by 1.2, that is scaled by 1.2, but this here is a material property. It's not scaled by anything, and therefore to make the equation still remain at 1, sigma AR cannot be scaled by, again, 1.2. It simply will not work. And that's why you have to again go in and, given these values, calculate sigma AR independently. And that's what it will come out to be. Now, once you have that, then you can go and, because we know the values of sigma F prime and B from the previous example, so I'll just put a check there and there, we can go ahead and calculate an F2, which we find to be 17,518 cycles. So now you can go and set this equals 17,518 and finally determine the value of N2 by invoking Palmgren minor. In other words, failure occurs when accumulated damage hits 1. And N2 will be found to be 11,393 cycles. So this example says that if we had only the first interval of loading, then we could cycle 143,000 cycles. If we had only the second interval of loading, we could cycle for 17,518 cycles. Less because the loading in the second interval is larger. But now what we do is we only cycle 50,000 in the first and 11,393 in the second, and we get fatigue failure again as predicted by the Palmgren minor rule.